signal from time to frequency domain, or we use inverse Laplace to transfer a signal from frequency to time. Now, besides signal, we want to talk about the systems, all the systems which are around us. No matter what's the mechanical, electrical, or any other type of system. We can put any system in a box which represents the system in a time domain. And of course, you can have an input to this system and get the output y of t. And assume this system do the operation of t, capital T. So this capital T here doesn't have any mathematic meaning. I just want to show you that some operation is happening inside this system, okay? So the output, of course, would be the effect of this operation on your input signal. So we can write it as t of x of t in time. So for now and for rest of the course, when we talk about the system, we will talk about a special group which are linear time invariant systems, or in short, LTI systems. What are linear time invariant systems? If you have a system which is linear and time invariant at the same time, we call it LTI. What I mean by linearity when we talk about the linear system. So for any system, of course, you can have single input, single output, or multiple input, multiple output. Assume, for now, we have only 2 inputs and 2 outputs, corresponds to this system. If you insert the linear combination of x1 and x2 to the system with some constant coefficient a1 and a2, if you get exactly the same linear combination format for the outputs, then we call them linear system. And then you have a system which has the linearity property. So as you can see, linear combination of the inputs, I have the exact linear combination in the output part. How about time invariant? A system is time invariant that if you put the input to the system with t0 delay, you get you see the same amount of delay in the output as well. So t0 delay or shift in the input and t0 delay or shift in the output. Yes, please.
So you're talking about some sort of, you put an input into a machine and the output is the same thing, or
if you input the input to the system with a delay,
yeah.
For instance, instead of putting the impulse to the system at time 0, you insert it at time t equals to 5. If you see the exact 5 minutes of delay in the output as well, then you have time invariant.
Okay, so you need
the same amount or the same effect you implement in an input, you see the exact one in an output. You can see I have t minus t0 in both x and y. So same delay inputs, you see same delay in the output as well.
But why isn't it just the same then?
Not always. If it's LTI, yes. If it's a linear time invariant system, yes. But we can have some other type of systems as well.
Okay.
We will not cover them here.
Okay.
Yeah. So that is LTI system, linear time invariant, when it has both property together. So this is a signal, the system in time with input signal in time, output signal in time. Now I want to shift the whole system or transfer the whole system from time to frequency. From time to frequency, we know we should do some sort of Laplace. So x of t will become capital X of s, and y of t will become capital Y of s. But what will happen to the system, to the operation which is inside the system. You can represent or show this question mark by a function which we call it transfer function. And the notation for it is h of s. How we find this transfer function? The transfer function, or h of s, is always and always the Laplace transformation of your output divided by Laplace transformation of your input. This is how the transfer function is defined. And actually, if you do the math correctly and find the right transfer function, this transfer function represents the exact input and output behavior you have in a time. So they match, and they have to be this way. And this is the name in Danish for transfer function. I will not pronounce it. So just you do it yourself. Okay. So now if you get the transfer function of your system, you can use it to obtain the output of the system in frequency as well. Why? Because based on this equality, you can write capital Y of S is your transfer function by your input in frequency. So then you have, or you can use it to obtain the output in a frequency as well. And I have it in the slide there as well. Any questions so far? If you want to take a picture of this, do that, because I want to use this board again. I need
Can you maybe explain what I want to see how you get from a differential equation. No, double y, no, y to the power of double t plus 3 times. The example you put up there.
Oh, you're talking about this one now?
Yeah, but the thing is, how is that a frequency?
Let me see if I have any example for today. No, not for today.
Because I cannot see. If I'm thinking about a frequency, it's like a stable number or something like that. But how is that in the final form a frequency or a time or something like that?
So you cannot see how this is, or how this frequency is related to this time?
Yeah, it's just yeah, I don't get it. How can you say frequency? Frequency is like hertz or something like that.
Yeah, and I don't know if you have been here last week or not, but we looked at this short video which the guy explained.
Yeah.
Also, when we are in a time, of course, it's clear for us what we're talking about. But when we are in a frequency, we look at the amplitude or a spectrum of a signal. So they are completely different. And for any signals has a representation or format in a time and a specific format in a frequency as well. So I don't know how should I explain it, but
it's just how it is. Yeah.
It should be.
Okay.
For instance, for unit step function, which is this one, in time, when we are in a frequency, it will be 1 over s always. So if you plot the 3D of this in MATLAB, for instance, you could see how it represents. They represent all unit step, but one of them in time and another one in frequency. I try to generate the MATLAB code maybe in a break and show you after that.
Yes.
Any question for this one? Okay. Okay. So now use is called small h of t, and we read it as the impulse response of the system. So impulse response of the system. So if you put direct delta as an input to any system, the output will be always the impulse response, or small h of t. Now, again, I want to transfer all of this to frequency. I check the Laplace. So here I have the Laplace of direct delta of t, which we know is 1. The result is 1. You can use the tables or you prove it. It will become 1. And here I have the Laplace of h of t. Okay. Now, can you remember, I just erased it, that I wrote that output is always the multiplication of transfer function for my Laplace of your input? I want to use it here. So the Laplace of output, which in this case is the Laplace of transfer, this response, impulse response, is equal to your transfer function of the system times the Laplace of the input, which for direct delta or impulse is 1. So this is always valid, so we should keep in mind that the Laplace of impulse response would be always and always the transfer function of your system. Actually, I have it here as well. So you can see in this line, the Laplace of impulse response would be always transfer function. And of course, we can do or move from right to left as well. And if you have the transfer function of your system and you do the inverse Laplace of it, you get the impulse response of the system. This is something which you will use them in the exercise or maybe in exam. So just highlight it for yourself or keep in mind that this equality is always valid. And you can do both sides, from left to right or right to left. Okay, any questions so far? Yes, please.
Is input response a general term in terms of systems? Or
Yeah, if the input is direct delta or impulse signal, the output always called impulse response. Even in signal handling codes, you will hear this term, yeah. Okay. So now let's look at much more general linear time invariant system. Any general LTI system, if you're working with a mechanical system, you can write Newton's laws for them. If you use or work with electrical system, you can write the Kirchhoff's law, voltage or current law, and obtain the differential equation of the system. I don't know if you have done it in other math courses you have so far or not, but you can use these rules or laws to obtain the differential equation of the system. So in a general case, we can write the differential equation of the system in this format, as you can see in the middle, the first equation from the top. So in the left side of equality, we have the differentiation with respect to y, and in the right side, we have the differentiation with respect to x. So we know that to find h of s, which h of s was the transfer function of your system, we need to have the Laplace of output over Laplace of input. So if we make the Laplace from both sides of your differential equation, like what I did here for this example, we took Laplace from both sides. If you do that, and then make the factorization of capital Y and capital X, then this is the general formula for Laplace transformation of any system. So the Laplace of output over Laplace of input, this is the general formula. Now, during the last 5 years, which I was responsible for this course, I saw sometimes which the students were confused. Why? Because you can see here the coefficient of capital Y of S are these A terms, and the coefficient of X are these B terms. And the students, when I say it's the Laplace of output over Laplace of input, they think that now the A's should come at the top and B's should come at the bottom. But actually mathematically, I can prove it here to you or show you in a very simple example. They have to be reversed. So don't make this mistake in exercise or exam. I will show you in a second in a simple example why they switch the place. But if you have, or you are in this line, just put the coefficients of y in the denominator and put coefficient of x in the numerator, and you are done. Let me show you in a very simple example. This is again one random example. Assume we have this one. Okay. And I want to find transfer function, which is the Laplace of output over the Laplace of input. So I need to have y of s divided by x of s. Mathematically, if I want to do a right and correct mathematic way, you can see here I have y of s. In order to have the division of y of s by x of s, I multiply the whole term by 1 over xs. So if I do this multiplication, what I get? It becomes s2 plus 6x plus 5, then y of s multiplied by this one, so I have it now here, equals to, I do the multiplication to this side as well, and this will cancel out by this one, so I don't need to write it anymore. And I'm looking for this term. So y of s divided by x of s. Again, if I want to get this one, I should multiply this by the coefficient of it. So you can see, in order to find the transfer function, the coefficient of y, now it's in the denominator, because it should be, mathematically this is how we obtain it, and the coefficient of x we have here in the numerator. Again, don't make this mistake later on, because I have seen it a lot. When you want to find the transfer function, instead of doing the way I did, multiply by this and so on, just take the coefficient of y of s, put it down, and coefficient of x and put it at the top. Then you have the transfer function. Is it clear for everyone? If it's not, just ask. Which part?
No, I was just because you said, I feel like you said, don't do this, but it's just
No,
because...
no, you can do that.
It's just
the part
more
which I
complicated.
said you don't need to do is multiplication by this one, because now you know the logic. So in your head, just switch the coefficient location, and then you have it. But if you are...
Yeah, if in doubt, you can always do
You
the
can do
math.
that, yes. If you are in doubt, just follow what I did here. Okay. So, I think this is the last slide for today. So when we have your transfer function of your system, like this one, we can find the poles and zeros of your transfer function. What are the poles and zeros of a transfer function or any system? The poles of your system is the values of s which makes the transfer function infinity. This is the definition in front of the poles. So let's look at here. So I need to find, for poles, I need to find values of s which make h of s equals to infinity. infinity. Yes?
When the denominator goes towards 0.
Exactly. So if you put the denominator equals to 0, so s2 plus 6x plus 5 equals to 0, and find the solution, then you have the poles of your system. And here you can see in the transfer function h of s, I wrote the denominator equals to 0 in middle one. So for poles of the system, we always put the denominator of the transfer function equals to 0 and find the solution. And then you have the poles.
What?
Yes?
What is the poles? How can you
How
teach
can
that?
we use them?
Why
We
would
will
you want to
use
find
them to check if the system is stable or not, which is next week.
Alright.
But you can also use them again to check the stability when you want to design a controller for your system, such that if the system is unstable, you use a controller to transfer it to the stable system. Yeah. The last definition or term for today is the zeros of the system. The definition of the zeros are the values of s which make the transfer function 0. So for zeros, I need to find the s which make h of s equal to 0. In which scenario or case this becomes 0? Yes, please?
S equals to minus 5.
Exactly, when the numerator is 0 or h is minus 5 in this case. So h or s plus 5 equals to 0. So again, here I have when the numerator of your transfer function becomes 0. So if you put the denominator equals to 0, you find the poles of the system. And if you put the numerator equals to 0, then you have the zeros of the system. And I think that was the last slide for today.